LCR circuits. L is for inductor, C is for capacitor, and R is for resistor. And I can never remember whether it's LRC circuit or LCR or CLR, CRL. In fact, if you Google it, there's all sorts of combinations. Some people call it CLL. I think LCR is not very widely used. I think LRC is more used. I don't know. But if you want to find more about this circuit and you fail to find much in Google, just change the order of the letters and you're going to find it, okay? All right. So the system is like the following. First you have an inductor. And it's basically a coil, right? And then there's the capacitor. And then there's the resistor. And then we assume that there's an external voltage source. All right, so the voltage drop across an inductor is equal to, what does inductor try to do? It goes against the change of current, right? When the current tries to change, it changes the magnetic field inside this coil, and that gives you an opposing current, right? If the current tries to change, the magnetic field appears and it gives you an opposing current, right? And the formula for that is it's a negative L change of, it's the change of current. It goes against the change of current. That's the voltage drop across an inductor. How about voltage drop across a capacitor? Well, this is more known as in the following form. Amount of charge is equal to, in a capacitor, Q is equal to C V.
Oh, yeah.
Yeah. Remember that? Yeah, okay. See, everything is related. Don't think that you can study one subject and just completely erase it out of your mind and never to see it again. You really need to remember things like this, okay? So if you divide this C to the other side, you get the following formula. It's 1 over C times Q. And it's actually a voltage drop, so this is how we're going to write it. And the voltage drop across a resistor is the famous Ohm's law. What is it? V equal to? IR. Very good. That's what we have. And then if I say VE is the external voltage, the voltage source, then there's the Kirchhoff's rule, right? Kirchhoff. Yeah, I don't know which is right. Kirchhoff. Okay, I'll follow you. Kirchhoff's loop law says that if you go around the loop, the voltage adds up to be 0, right? So you have V minus L di over dt minus 1 over C Q minus IR equal to 0. And then if I move everything to the other side, I get the external voltage. I just realized, I think people usually write this as E of T. I think that's the standard letter that people use for this. Okay? And then if I move it to the other side, it's L di dt plus 1 over CQ plus IR. Okay.
Shouldn't that L be negative because don't you have it as negative L?
No, I'm moving to the other side, so all of the negatives will be.
Oh, whoops! I'm
be
sorry, I
positive.
didn't see negatives next to
Yeah.
everything else.
So it's equal. All right. Now, this has actually two unknown functions working at the same time. There's the I of t. This is, we're assuming that the current is changing with respect to time. But the charge inside the capacitor is also changing. See, capacitors, they become charged and discharged all the time, right? So this is a function of t. And in order to make this as a function, a differential equation for a single function, what we do is, I want to differentiate everything. And when we differentiate, we're going to assume that the inductance, capacitance, and resistance, these values, L, C, and R, are constants. So we don't have to use any product rule or anything. So let's differentiate it. If I differentiate, this is L, this is a single derivative, so it's like two derivatives. And then 1 over C, what's the derivative of Q? Do you know? What's the change of current with respect to time? No, what I said it. What's the change of charge with respect to time? That's current. And I said something wrong. Okay. I prime times R. Okay. And then we replace this Q prime by I, and let's write this on this side. Li double prime plus Ri prime plus 1 over C times I equal to E prime. Okay? So this is the equation for LRC circuits or LCR circuits or whatever, okay? I guess LRC sounds better, LRC. I'm going to call it LRC circuits. Now, this is a second order equation. And it looks very similar to the mechanical vibrations that we've done before. Okay? How does the mechanical vibrations equation look like? Mx double prime plus Cx prime plus Kx equals to F of t, external force. Okay? So you can make an analogy between the two systems. Two systems analogy will be like the following. Inductance is like mass. Resistance is like the resistance coefficient. Similar, right? And 1 over the capacitance is like the spring constant. And the external, the derivative of the external voltage is like the external force. And one of the things that people are interested in is, if you solve this system, IT will be written as, again, the I transient plus I steady periodic. And in most cases, your external force is, external voltage is periodic. There are two instances. One is actually if you have a regular AC power, this will be periodic, right? Another instance is when you have a radio system. So in any kind of radio system, you always have this type of circuit because the radio waves is acting on this circuit through an antenna like an external voltage source, okay? And in that case, instead of trying to minimize resonance, in that case you would want to maximize the resonance, right? Because maximizing the resonance means you have a good signal. Okay? So the practical resonance that we didn't like in the mechanical vibrations is actually a good thing when it comes to picking up radio frequencies. Right? So, so IT is I transient plus I steady periodic, where I transient is basically the complementary solution which dies quickly to 0, and really what survives is I steady periodic, and the I steady periodic happens to be happens to look like the following. I steady periodic will be having an amplitude times cosine of this omega naught t minus alpha, where if this is like epsilon naught cosine omega naught t. So this is if omega naught is the external frequency of the external voltage, then if it's the angular frequency of the external voltage, then the current on this circuit will also have the same kind of frequency, but it will be trailing the external voltage by some angle. Okay, and that's another thing that in your E class you'll be interested in. Okay.